Hello, class. So on this video, we'll continue on the first chapter of differential equations. And in particular, we're talking about this subject called just properties of differential equations. We saw a couple things. We saw what a differential equation is. We also saw what it means to solve a differential equation. Right? We saw that a solution to a differential equation is a function that when you plug it in, you get equality. We did some examples of that. And so we verified that given this differential equation, dy dx equals 2, we verified that y equals 2x is a solution, y equals 2x plus 7 is a solution, but y equals e to the x is not a solution. And the way we did that, we just plugged it in, and we should get equality. Or whatever was on the left of the equal sign should be equal what's on the right. Should be equal to what's on the right. And we did another problem that looked kind of complicated, but it was just verifying. So we're given this differential equation. We wanted to verify that x to the fourth, this function was a solution. And again, it was just plugging everything in, right? So replace the dependent variable y with a function, in this case, x to the fourth, which is what we did in this line here. And then just from there, just simplify. Take the second derivative of x to the fourth, etc. We simplified everything down, and we got 0 equals 0, right? So x to the fourth is a solution to this differential equation. Now, what this tells us, and that I mentioned in the last video, is that given a differential equation and given a function, it's very easy to verify whether this function is a solution, or just plug it in. The thing that I mentioned is that it's not as easy, and in fact, this is the meat of differential equations, is given a differential equation, you're not given a solution. How do you find a function that satisfies it? So you're not given the function, you have to find it somehow. And if you look at a differential equation like this, you'd be like, well, how am I going to find a function that satisfies this differential equation, that's a solution, if I weren't given that x to the fourth is one such function, right? So that is where differential equation starts getting hard. Now we'll get to functions that are kind of complicated like this one. But before we do that, let me make a note here. So the independent variable is important, right? So I keep talking about independent and dependent variables. So let me just make it clear that when you have an expression like this, y is a function of x, then the dependent variable is y. It's the one that depends on x. And the independent variable is x. In this case, the names might change. Right? So for example, we could have something like x is a function of t. Right? So the names changed, but you should still be able to identify that now in this case, x is the dependent variable because it depends on t, and t is the independent variable. Now this is going to matter for a lot of things. I'll show you in a couple of slides one reason why this matters. But it matters because it's different if I write dy dx, for example. It's different to if I write dy dt. Right? We're taking the derivative of y with respect to two different independent variables. These two things are different most of the time. So just keep that in mind, right? I'm going to keep saying dependent and independent variables, and make sure that whenever you hear those words, you realize what it is that I'm talking about. Just a quick note. Now, let's go back to finding solutions to a differential equation. Again, if you're given a differential equation and a function, it's very easy to verify whether this function is a solution. So what if instead we're just given a differential equation and we want to find a general method to find a solution for it? Okay. So let's go back to, again, this very simple differential equation, dy dx equals 2. I want to find or derive a method that's going to give me solutions to this differential equation. As we saw, this differential equation can have more than one solution. We saw that in the previous videos. So what's the general method? So we're trying to find y, right? A function that when we plug it in satisfies this differential equation. Now we're taking the derivative of y. Okay? Now if you remember from calculus 1 and even calculus 2, there's this nice relationship between derivatives and antiderivatives. Basically, if you have a function, you can take its derivative with respect, and actually let me just write dy dx just to make the variable clear. You can take its derivative. Now, let's say you want to go back to the original function. So Let's say now you start with the derivative, you want to get to y. Okay, so we want to go this way instead. So how do we do that? So one way we take derivatives. So this way is derivative. So if you remember from Calc 1 and Calc 2, the way to go backwards, or the way to kind of undo derivatives, is with this operation called an antiderivative, which in calculus 1, we would denote like this. Integrate the function dy dx with respect to x. Of course, this notation here doesn't mean just one function. Remember, this notation means all functions that whose derivative equals dy dx. So for example, just as a refresher, if I had the integral of, let's say, x squared dx, remember we would write that this is equal to x cubed plus divided by 3 plus a constant, because there are infinitely many solutions, right? Or infinitely many functions whose derivative is x squared. The nice thing is all of these functions differ by a constant, right? So all you have to do is find one function whose derivative equals x squared, and then how do you get all of the others? Well, just add a constant. Right? So that's what you learn in Calc 1, right? That's the fundamental theorem of calculus. So this is kind of giving us a general method to find solutions to differential equation. We want to undo the operation of derivative. So how are we going to do that? Well, we're going to integrate. Now, whatever we do to the left-hand side of an equation, if you remember from algebra, you want to do it to the other side as well. So if I integrate the left-hand side with respect to x to get back to y, I have to integrate the right-hand side with respect to x as well to keep everything equal. So let's see what that looks like. So again, we have this differential equation. We want to undo the derivative, so we're going to integrate both sides. And again, here, the independent variable matters, right? I want to integrate with respect to x because I'm taking the derivative with respect to x. So again, here I'm using the implied symbol to the integral of dy dx with respect to dx. And again, whatever I do to one side of the equation, I have to do to the other. Now, what's the integral? What's an antiderivative for dy dx? Well, we know easily what an antiderivative is, at least one of them. Well, y is an antiderivative to dy dx, because by definition, dy dx is the derivative of y with respect to x. So to find what this left-hand side is, again, by the fundamental theorem of calculus, just find one such antiderivative. Y works, y is an antiderivative, and then you add c. And now all functions whose derivative is dy dx have this form. We simplify the right-hand side. The integral of 2 with respect to x is 2x, and of course, plus a constant. Now, the last thing I'm going to do here is I'm going to move the constant, because I want to keep y by itself. Remember, we're trying to solve for y, so I want to have y by itself. So I'm going to write this as y equals 2x plus, and I'm going to subtract c from both sides. Now, these constants, d and c, they can be any constants, right? There's no restrictions on what they are. So usually what I'm going to do in terms of notation is whenever I combine two constants, which are arbitrary, I'm going to combine them into a single constant. And usually I'm just going to use the letter c. And again, all I did here was combine these two constants into this new constant and just call it c. It's kind of like abusive notation because I am calling it c here and I'm calling it c here as well. But I hope you can understand that if you have two arbitrary constants, if you add them, subtract them, multiply them, divide them, you just have to be careful with division because you can divide by 0. But in any other case, you can just combine them into another arbitrary constant. And for most purposes, I'm going to call that constant c. Okay. So now we reach the point that we wanted because now we know what our function is. We want to find solutions to this differential equation. We went through this process of understanding that, okay, I'm taking derivatives to, in this differential equation. I want to undo that to get back to the original function y, and I undo that by taking definite integrals of both sides. After you simplify all that, you get, Okay, what are solutions to this differential equation? Well, functions of this form, 2x plus c, which if you remember matches what we did in the example here, right? We saw that y equals 2 times x is a solution, y equals 2 times x plus 7 is a solution, and in general, y equals 2 times x plus any constant is a solution to this differential equation, dy dx equals 2. Okay? So in general, this is what we're going to try to do. Given a differential equation, our goal is going to be, can we somehow integrate both sides of the equation to undo the derivatives and get back to our function y? Okay, that's the general idea. Now, of course, this is a very simple example, but we're going to build up from here. Okay. So in conclusion, what is the method? Well, integrate to get rid of derivatives. Okay. So I'm going to stop here, and then we'll continue talking about some other properties of differential equations and some definitions that I want to introduce formally in the next video.